So let's start with the third part of linear regression. Now, as we have seen, linear regression is used when we want to predict the value of a variable based on the value of the another variable. So the variable we want to predict is called the dependent variable or sometimes the outcome variable. Now, let us continue with our exercise that we were doing. So let's start first importing the libraries, required libraries, that is pandas, numpy, giving the same command which we have seen earlier, that import pandas as pd, import numpy as np, import matplotlib .pyplot as plt, which is of course for graphics, for graphs and charts, etc. Then cborn for further addition to that as cborn instance. Then from sklearn.model, model selection, import train test split, because for training and testing the data you need this. Then from sklearn linear model, import linear regression, because we have to use linear regression. Then from sklearn import matrix, what matrix we are going to use, and then matplotlib inline. So these are the libraries that we will be using, right? Now the following command imports the data file, data set, that is which is in CSV file. Now data set is equal to pd.read CSV, because it is a CSV file, and whatever location data file is, that should also be mentioned, like c:weather.csv. Then let's explore the data. It is very important, as we have seen earlier also, that we must explore our data to understand it better and better about what are the various attributes of the data set. So when you give this command like dataset.shape, you will get this kind of a response from the system. Should receive output as 1,19,040 rows and 31 columns, which means the data contains 1,19,040 rows and 31 columns are there. To see this statistical details of the data set, you can also write dataset.describe. So this will give you other details like mean, median, standard deviation, percentiles, etc., etc. And next, we can also plot our data points on a 2D graph to eyeball or our data set and see if we can manually find any relationship between the data using the below script. So we can write further this kind of a script, dataset.plot, x is equal to minimum temperature, y is equal to maximum temperature, style is equal to O. Then plot title, minimum temperature versus maximum temperature. X label is minimum temperature, that is x axis, y axis is maximum temperature, and when you write plot plt.show, this kind of a graph will be shown on your screen. We have taken minimum temperature and maximum temperature for doing our analysis. Below is a 2D graph between minimum temperature and maximum temperature, right? So to check that what is the average maximum temperature, and once you plot it, we can observe that average maximum temperature is between 25 and 35. And for that, again we can write this kind of a code, plt.figure, fixed size 15,10, then plot tight layout, and then cborn instance, and then you will get this kind of a graph on your screen. So this is how you can get that's why it is very important to draw these kinds of a graphs, which is also known as data exploration. You are trying to understand your data as in a much better position, which is very, very important. Now the next step is to divide the data into attributes and labels. Attributes are the independent variables, while labels are dependent variables whose values are to be predicted. In data set, we have only two columns. We want to predict the maximum temperature depending on the minimum temperature recorded. Therefore, our attribute set will consist of minimum temperature column, which is stored in the x variable, and the label will be maximum temperature column, which is stored in the y variable. So you can see that x is equal to data set minimum temperature values, reshape -1, 1, and similarly y, again data set maximum temperature dot values, reshape -1 to 1. So next we will split the data. Now we split 80% of the data for the training purpose, and the 20% that we are going to have is for the testing. So both these things are important, because first you have to train your data, and then whatever data that you have kept for testing, on that you are going to test it. So the test size variable is where we actually specify the proportion of the test data, and this can be varied. It's not mandatory that you can always have 80-20 ratio. You can have 70-30 or 60-40 or whatever. So you can write this kind of a code like x train, x test, y train, y test is equal to train test, split within quotes capital X, y test, size is equal to 0.2. 0.2 means that it shows that 20% of the data has been kept as the test data, and random state is 0, which means that the iterations is only 0. There is no iteration in fact. And this is the way in pictorial representation you can see the training testing has been divided. Then after splitting the data into training and testing sets, finally the time is to train our algorithm. For that we need to import linear regression class. That is why we imported the linear regression, if you remember in the beginning when we imported various libraries, and instantiate it and call the fit method along with our training data. So linear is equal to regressor is equal to linear regression, regressor dot fit x train y train. This is the training of the algorithm. And then, as we have discussed, that the linear regression model basically finds the best value of the intercept and slope, which results in a line that best fits the data. To see the value of the intercept and slope calculated by the linear regression algorithm for our data set, execute the following code. Now we are going to write this code for further doing the analysis. So to retrieve the intercept, print regressor intercept for retrieving the slope, and print regressor dot coefficient, that is COEF. So you will get this kind of a line. Now the result should be approximately 10.661, 85201 and 0.920339997 respectively. This means that for every unit, 1 unit of change in minimum temperature, the change in maximum temperature is about 0.92. Now this is what the indication is from this kind of a result that you get. Now that we have trained our algorithm, it's time to make some predictions. To do so, we will use our test data and see how accurately our algorithm predicts and the percentage score. So to make predictions on the test data, execute the following script. That is, y prediction is equal to regressor dot predict x test. X test is taken because the x, that is the test data that we have kept it for the testing purpose. Now compare the actual output values for x test with the predicted values. So now we are going to make a kind of a comparison between the two, and so for that we execute this script, that is df is equal to pd data frame actual y test flatten, then predicted y pred flatten, and when you write df, then you will get this kind of a output, that is actual versus predicted. And you can see that there is not much variation. There is definitely a variation. It cannot be same, but certainly you can easily say that they are very close. Like actual is 28.88, predicted is 33, then next is 31.11, 30.09. So like that, if you go from top to bottom, you will see that the difference is not very wide, and that is why we can say that it is the actual and the predicted one is quite close and maybe correct. So comparison of actual and predicted values are in front of you. We can also visualize comparison results as a bar graph using the below script. So you can write this script also, and then a bar graph can be drawn. So as the number of records is huge for a representation of representing this thing, so I am taking just 25 records. So because the more record, that means it will be very congested, so you will not be able to make out anything. So that is why only 25 records are taken. So df1 is equal to df head 25, and then in the data frame 1 plot kind is equal to bar type, fixed size is 1610. Then again you can create a grid if you want. So for that we have written plt.grid, which measure lifestyle is equal to line width 0.5, color is green. Similarly, the next line, that is plt grid, which minor, and then line style, line width is equal to 0.5 and color is black. That is for the grid. Then when you want to show the plot, you have to write plt.show, and you will see that this kind of a graph will be in front of your screen. This will be coming up. So bar graph showing the comparison of actual and predicted values. Now let's plot our straight line. Now that was the graphical representation, that means visualization. Now here we are going to draw a line graph. Now here the scatter graph, so to say. So PLT scatter, X test, Y test, and color is equal to gray, because we want this to be presented in a gray color. Then PLT plot, X test, Y prediction, and then color is red. Then that is for the line, and line width is given as 2, so that it becomes slightly broader. And when you write PLT dot show, the graph will be drawn as it is seen in your screen. So this is your prediction versus test data. Now the straight line in the above graph shows our algorithm is correct, and the final step is to evaluate the performance of the algorithm. Now whatever we have done, it's fine, it is giving us the results, but now we also want to check or rather evaluate the performance of the algorithm that we have developed. So this step is particularly important to compare how well different algorithms perform on a particular data set. So for regression algorithms, 3 evaluation metrics are commonly used, right? So you can see that these 3 metrics that we have, first is mean absolute as error, that means MAE is the mean of the absolute value of the error. This is for the manual calculation. We are not going to do that, but we must know that what is the formula used here. So MAE is equal to this formula which is mentioned, 1 upon n sigma j to 1, j is equal to 1 to n, and yj minus yj. So this is the kind of formula for mean absolute error. Similarly, for mean squared error, this formula is used. MSE is equal to 1 upon n, and then again sigma 1 to I to j, I to n, and yi minus yi to the whole square. And then there is another formula for root mean squared error. It is the square root of the mean of the squared roots, and for that this formula is used. RMSE is equal to 1 upon n sigma j is equal to 1 to n yj minus y hat j whole square, and this is root mean squared error. So luckily we don't have to calculate manually. So that is why we have imported scikit, sklearn library, which is very, very handy for all such complicated calculations. Otherwise manually it is just impossible, kind of impossible. It's not impossible, but certainly it's not that easy. So that is why this kind of libraries can be used, and we can do all such complicated calculations. So this is how we can calculate our forecast or prediction. This completes the 3rd tutorial in linear regression. So thank you for that, and we'll now move on to the last tutorial. Thank you.